In today's video, we'll be looking at some of the basic maths in biology. Now, a lot of these equations here, you will probably have to memorize before the exam. They won't be given to you in the paper. So, but the thing is, here I'm going to focus on, first of all, what the equation would be and what the symbols in the equation actually means, and then in certain cases where possible, I will show you an example. Okay, so here we go. So first of all, we'll sometimes have to calculate the circumference or the area of a circle. So just make sure you memorize, these are GCSE maths, the circumference is talking about the outline of the circle. So we calculate as 2 pi r, r standing for radius. And the area will be pi r squared, okay? So if we look at this particular example here, here we got the circumference and that's the radius. And we've got a ruler here that I'm going to measure. And let's say I'm going to be looking at millimeters in particular. So if I'm looking at that, that's about 35 millimeters. Then therefore, I would know that the circumference would be 2 pi times 35. And therefore, if I just put it in the calculator here, then I would get 219.9 millimeters, like that. And that would be my circumference. Whereas my area would be pi r squared, so therefore it will be pi 35 squared. And therefore, quickly in the calculator, 3,848.5 millimeters squared, like that. So that's how you would lay it out. It's worth noting that apart from knowing what the symbols actually mean, it is quite a good thing to show you're working, because sometimes even if you, let's say you made a mistake in your calculation when you're putting the numbers into the calculator, but the examiner will see, okay, you've got the wrong answer, but then you've got the right working, so you'll probably get 1 mark for the correct working, and then you'll get the 2nd mark only if you got the right answer sometimes to the right decimal places or significant figures, because they can also take you mark off for that. A cuboid, on the other hand, will be a material that looks like this. So sometimes I could say that a particular bacteria would probably have the shape of a cuboid or shape of a cylinder. Then you just make sure you need to know how to calculate that. So here we've got the cuboid surface area. So if you know how to calculate the area of a square or rectangle, all you need to do is to work out how many different sides there are. So in this case, I can see that this is roughly a square. So that would be x times y would be that particular area there. But because I have 2 ends of that, so I need to times that by 2, hence 2xy. Then on this particular surface here, so we've got h, or I'm referring it to as the height. Then the side would be x, so that would be x times h there. But because we've got 4 sides of it, therefore it times it by 4. So the total surface area would be 2 of this side plus 4 of that side of the area. So that's how we work it out. As for volume, you would know it would be the base times the height times the length of some sort. So in this case, x, y, and h, right? Base times length times height. And now let's have a look at the mean, right? So sometimes mean would have this particular symbol where, well, specifically the line above it. So it could be n with a line above, which means the mean of n, or x with a line above, meaning the mean of x. So obviously it's the sum of all values divided by the number of values that we have. So let's look at this example. For example, calculate the mean resting heart rate of the following patients. So let's say patient A, 71 beats per minute, patient B, 67 beats per minute, patient C, 82 beats per minute. So therefore, I can say that the mean resting heart rate will be 71 plus 47 plus 82, because I've got 3 patients here, 3 data values, so therefore I divided it by 3. And if I put the numbers into calculator, that would equal to 73, let's say to the whole number, beats per minute, like that. It's also worth noting that sometimes they say, oh, can you suggest a way to improve the experiment? Then you can say, oh, we can repeat the experiment and then calculate a mean. Now, just notice, whenever you say to repeat an experiment, you must follow up with calculating mean. Sometimes they won't give you the mark unless you mention both repeat and calculating the mean. And also, you can't say calculate an average, because an average could be a mean, mode, or medium. So you have to say it's the mean in that particular situation. So here we've got rate. This is a very commonly asked calculation question. Rate simply means the speed or the velocity at which something occurs. So it could be a reaction, which is most often the case. So the rate is the change, which is calculated by the final value minus the initial value divided by the time that's taken for that change to occur. Notice that rate, depending on if it's per minute or per second, then you can obviously have a slightly different unit. Here are some specific examples relating to some of the biology. So, for example, if you're measuring the enzymatic rate of reaction, then you can either measure, so set an experiment to measure the loss of the reactant or the gain of the product. So, for example, investigating the action of catalase on breaking down hydrogen peroxide. So, an easy way to do that is to measure the gain of oxygen, which is produced by the breakdown of hydrogen peroxide. Depending on the actual reaction, you have to then decide which one you're actually going to measure. For diffusion rate, it could be, let's say, the distance traveled by whatever substance that it is working with. So if it's a diffusion experiment using hydrochloric acid with agar cubes with the phenolphthalein dienzide, then it could be about the distance traveled, distance of discoloration in some sort, depending on what the question is looking for. If it's breathing rate, then obviously the number of breaths taken per certain amount of time. Transpiration, the loss of water vapor by evaporation, usually set up as a potometer experiment. Then you can measure the distance moved by the air bubble in the potometer and then divided by the time taken during that movement there. Then it comes to photosynthesis and respiration. Then thinking about the equation of these two reactions, then you know that we can measure kind of similar to this one. So if it's photosynthesis, you can measure the release of the product, which is oxygen, or the loss of reactant, which is carbon dioxide. In this case, perhaps that the oxygen might be an easier way to do so, but it depends entirely on how the experiment is set up. If it's respiration, then it could be the decreasing oxygen and the increase of carbon dioxide. Again, depending on the situation, you might choose to do either one of them. Obviously, make sure you know that once you've measured all of this stuff, you have to divide them all by the time taken for that reaction to occur. And that is rate of reaction. Here we have percentage difference, which is a very commonly asked question or calculation question in exams. But often people just don't remember the equation, right? So percentage difference is the difference, which is calculated by final value minus the initial value. Then this difference divided by the initial value times 100 if it's percentage. Notice that we're dividing it by the initial. A lot of people will divide it by the final. Just make sure you know, because we're comparing to the initial value to see how big that difference would be. So that's why we would have to divide it by the initial. So make sure you memorize that. And depending on the number, depending on the difference, then you can probably get a positive percentage difference or a negative percentage difference. If it's a positive one, that means that there is an increase in whatever that you're measuring. If it's a negative percentage difference, then obviously that would mean the decrease of something. A classic one that they will ask you about would be in an osmosis experiment, where you set up, let's say, different concentration of solutions, and you put the same mass of potato cylinders into each of them, and then you measure the change in mass. And then let's say the potato cylinder has an initial mass of 2.5 grams. After leaving it in pure water, it has a mass of 4.0 grams. So now you have to find the percentage difference. Sometimes people find it also tricky not to just remember the equation, but also actually knowing what the numbers are referring to in experiment. Or in a question. So I would recommend doing it this way. So actually either highlighting the information in the question, or you can just write it out yourself. So in this case, I know the initial mass is 2.5 and the final mass is 4.0. So I'm just going to annotate that. That's the final mass. So therefore, my percentage difference would be where I've got the final mass, 4.0, minus my initial mass, 2.5 grams, divided by the initial, which is 2.5 grams. Then it times it for 100 for the percentage difference. Then simply put the numbers in the calculator. 4 minus 2.5, again showing working, it's 1.5 divided by 2.5 times 100, it would be 60% difference there. So from the end result here, I can see that it is 60%. It's a positive change. That means in this particular scenario, we know that the potato mass has gained 60% of the mass. And the reason why that would happen in an osmosis experiment is because surely leaving in a pure water beaker, then obviously pure water would be very hypotonic compared to the inside the potato cylinder. Therefore, water is moving into the potato by osmosis, therefore potato gains mass. And that's how you want to explain the situation here. And now we're going to look at something that is not as common, but still we need to be prepared just in case they ask it in exams. So in this one will be, first of all, percentage yield. So sometimes we can say that you're doing an experiment, even in chemistry usually, then you are predicting actually based on this formula or based on this chemical equation, I can predict, or my theoretical quantity would be, I will get this much stuff that will be made. However, in reality, obviously experiments can have either some slight errors in the measurements, or whatever reason that the actual quantity that is gained is different from the theoretical quantity. So therefore, we need to calculate the percentage yield. Let's say we're doing an experiment with a plant, and then we're collecting the volume of oxygen produced. The theoretical value, or the theoretical volume of oxygen that would be collected, let's just say is 200 centimeters cubed. However, the actual volume would be 150 centimeters cubed. Therefore, my percentage yield would be my actual quantity, my actual value, which is 150, divided by the theoretical value, which is 200. And because it's a percentage, I times it by 100. So therefore, by putting the numbers in the calculator, then I would know that my percentage yield is 75%, meaning I've got 75% of what I predicted that I would actually get. Now, on the note of talking about experiments or theoretical yield, etc., then we can also consider relative uncertainty. This is perhaps a little bit more commonly asked than percentage yield, and people often tripped up on this one because we rarely talk about uncertainty. So what does it actually mean by uncertainty? So we're saying that even though you can be using any sort of equipment, so for example, a ruler or a measuring cylinder, and even though they're designed to give a precise measurement of substances for us to do experiments, we need to consider that they might be slightly wrong. So there is a window of error there, or window of doubt. So that's why we say that this is the percentage of uncertainty. We're uncertain if it is absolutely correct. So especially they would ask about relative uncertainty of a difference value. So meaning, let's say you started with measuring this much volume of liquid and then you measured it later on. At the end of it, you probably looked at it, how it changed differently. So you got a different volume, then we need to consider how the uncertainty might have been doubled. So this is why, because it's calculating a difference value, therefore we times the absolute uncertainty by 2. And in some sense, the absolute uncertainty is almost talking about the resolution, so what is the smallest possible thing. And usually we consider it as the half of the smallest division on an equipment. So if I'm looking at a ruler here, so the smallest division on my ruler is 1 millimeter, so the absolute uncertainty will be half a millimeter. Or perhaps in this particular situation here, I've got a measuring cylinder, and if we zoom in a little bit to see it, let's say this is 1 milliliter and 2 milliliters, then this one would be 0.1 milliliter. Therefore, that would mean that the absolute uncertainty will be a half of a milliliter, so a half of the smallest division. So let's just do this specific example. So let's say I'm measuring the volume of liquids using a measuring cylinder. So the absolute uncertainty we just said, because the smallest division is 1 milliliter, therefore the absolute uncertainty will be a half of that. So that would be 0.5 milliliters. And then if we have to find the absolute uncertainty of liquids A and B, then for A, first of all, because liquid A is 200 centimeters cubed, or 200 milliliters in some sense, then we can just simply do, because this is just about the individual one, then I still do absolute uncertainty, which is 0.5 milliliter, divided by the quantity measured, which is 200 milliliters times 100. Percentage uncertainty just for liquid A would be 0.25%. Whereas for B, it's still the same absolute uncertainty, it's still 0.5, but my actual volume is 150. So therefore, the calculations would be slightly different. So I just divided by 150, and then times it by 100, therefore it would be 0.3 recurrent. So I'm going to say 0.33%, like so. Then finally, let's just say I'm finding the percentage uncertainty of the difference in volume of A and B. So first of all, I need to find the difference in volume. So difference between A and B would equal 200 minus 150, which is 50 mil, like so. Then I would say the percentage uncertainty would be the absolute uncertainty, which is 0.5. We calculated from before, but because this time is the difference, so I do 2 times 0.5 divided by the quantity measured. The difference is 50, so I divide it by 50 times 100. So therefore, my percentage uncertainty of the difference would be 2%. And that's how we would work out this particular sort of calculations. So now here we get to standard form. Sometimes we deal with numbers that are either massive or numbers that are tiny. The thing is, if we're trying to write them out, it sometimes could be a little bit difficult to write out a number that has, let's say, 10 digits in it. So therefore, sometimes we can actually simplify that by writing it in standard form. So it's a bit of a quick way to present and a standard way to present something. And so it's always about the single digit number, either with some decimal places afterwards, times 10 to the n, which is how many, it's the order of magnitude in some sense. So let's look at this particular example here. So let's say this number here, it's 14,521. So therefore, I can present it as 1.4521 times 10 to the 4. So you can see it's a positive index. And if it's a positive index, that means in this current form, I can move the decimal place towards the right. And usually it means that we only use a positive index if the entire number here is bigger than 1. So 10 to the power 4 is basically 10,000. So I just move, or in a simple way, I can move the decimal place 4 times to the right to get back to the same value. So 1, so in this case, would be 1, 2, 3, 4. And I'll get back to the original number. Or if it's a smaller number here, then I get 3.45 times 10 to the minus 2. So in this case, we use a negative index if the number here is smaller than 1. And in some sense, I can just move this decimal place twice towards the left this time, because it's negative and smaller, then I get back to the same number here. And you can notice how it's always going to be a single digit here, and meaning that it can either be 1 point something or 9 point something. You can't have 10 point something times 10 to whatever. It has to be, the maximum number is 9 and the minimum number is 1. You can't have 0.145 times 10 to 5 either. That's not standard form. So minimum 1, maximum 9. Usually the reason why people get tripped up is people often know that it is a single digit, but then they ignore or neglected to read the question where they ask you to present it in standard form to, let's say, 3 decimal places or 3 significant figures. And they thought, just to be safe, I'll write everything out. That will cost you the mark. So make sure you read the question, see how many significant figures or decimal places do they want you to present it in. So for example, in this one, not 315, then I present it as, so I can move this decimal place. So 1, 2, 3, 4, 5. So it would be 3.15 times 10 to the minus 5 because it is smaller than 1. On this one, I have to move it that way. So 1, 2, 3, 4, 5, 6. So it's 4.298713314 times 10 to the 6. However, let's say I want to present it in 3 decimal places, then I just do 4.299, because I'm rounding it up that way, times 10 to the 6. So this is 3 decimal place. That would be how we do these particular things. Following from standard form, here is something called orders of magnitude. It really only came up once in last year's AS paper, so it's still quite unusual to get one of these questions, but it's quite simple if you just memorize the sort of the rule that we use. So let's just say if we have to compare two different values, because we already made it turn the numbers in the standard form into this particular format, then we really, for orders of magnitude, just look at this particular number, the 10 to the certain index there. So in this case, let's say it's 10 to the 4, and this one's 10 to the minus 2. The difference in the orders of magnitude would be basically 6, because you're going from 10 to 4 to 10 to the minus 2. The difference between them would be 6. So you can say in this case, let's say this is my starting point and it's becoming this, then you can say it is 6 times bigger, the order of magnitude. So simply looking at the index of the base 10 number and then just work our way back like that. Or here's another example. Let's say I've got 3.15 times 10 to the minus 5 versus 4.30 times 10 to the 6. So again, I'm going from, so let's say in this case, I'm going from 10 to the minus 5 to 10 to the 6. Then it would be, if it's going that way, then it would be 11 times bigger. Or if it's becoming smaller, then I can say it's minus 11 times order of magnitude, which is a decrease, if this is the initial and that's the final. So it depends entirely on which way around it would be. Right, here comes the final bit about this particular video, would be about logs, logarithms. So this is a interesting one. It's a lot of people kind of just found it a little bit confusing, and it doesn't come up that many times, but it's probably incorporated in a particular graph. So it's worth actually understanding what this means. So key thing is, some of the questions they might ask you is, if it's not a calculation question here, but simply saying, why do we use logs to present certain values? So it's about, sometimes it's specifically used if you are working with numbers or working with certain things that are growing exponentially. So, for example, there are two situations here that we can probably use it, either the exponential growth rate of bacteria, because they divide by binary fission, so they literally double every single time they divide, or it could be PCR, where the DNA strands are also doubling every single time. So when we're trying to plot a graph, so this is what happens. If you're trying to work with the actual natural number, so let's say we've got 10,000 bacteria, like literally 10,000 bacteria there, then you would see that the curve would be like this. And if it's a curve there, and the numbers could be sometimes so small that you can't really tell the difference, and it's very, very hard for you to plot that. So but the thing is, if we turn it into log, let's say a certain bacteria count, then the numbers become much easier to manage, and first of all, it becomes much easier to manage, and secondly, I can also plot a linear line rather than a curve. So it's actually making lots of the different analysis much easier. So in this case, if it's 10,000, if I log 10,000, it becomes 4, log 1,000 becomes 3, log 100 is 2, log 10 is 1, and log 1 would be 0. So numbers are actually a lot easier to plot, whereas this one, if it's just 0, 1, 2, 3, 4, whereas this one would be an exponential difference there. So two things really, making the scales on the graph much easier to work with and easier to plot, and to plot a linear line rather than an exponential curve. So this is some of the questions, these are some of the answers you can use when answering questions explaining why we use logs. And unless otherwise stated, but I would doubt this sort of happens, most of the cases will be using normal base 10. Another type of the question that came up in last year's paper was about presenting a massive number in log form. So here are the procedures in which that you will do. So let's say I've got this many bacteria and I need to present it in log form. So step number 1 is to put log. So you literally just type in log and then type in that number. So in this case, I just need to put in log, which is here, and then I just put in the numbers. So sometimes in exam, double check that your numbers are correct. Yep, and it's correct. Then I just press enter, and I get this number 8.761. So let's say it's 3 decimal places. But the thing is, if you just put it that way, it doesn't quite work, because if you just put that as your final answer, you're saying that this many bacteria equals that much, which is obviously incorrect. So you have to present it in the index as an index of 10, which is 10 to the 8.761, and that would be your final answer. Because actually presenting it this way, you're saying that this number is actually a simpler way of representing that particular number. So this is your final answer. It came up in last year's A2 paper, I believe, and one of the common mistakes is actually putting that, and that will give you 1 mark, and that will give you the other mark as well. So there you have it. So that's most of the basic common formulas or maths in biology that I could think of. And in some of the other videos, I'm going to cover more specific biology maths. So maths that you would find in AS biology and maths you'll find in A2 biology. But in any case, this particular video should be quite useful, no matter if you're doing AS or A2 biology, because it's going to be covered in any biology context. So be prepared.